Hi, I'm Owen McFarlane. Here's a couple questions. Does hitting gates while slalom skiing slow you down? If so, does that affect your speed enough to make a difference to your final time? Let's do some history. When ski racing was first invented, the poles in which participants must ski around were traditionally made out of bamboo. Bamboo was a great material as it was very rigid. However, as the sport became more and more widely known and speeds got faster, the bamboo gates were seen as dangerous, and in the 1980s, a new technology was introduced into the sport. Thus, the slalom gate was introduced. Slalom gates are tall and thin polycarbonate cylinders that have a hinge on the bottom, allowing them to move freely and be pushed out of the way of a skier as they bomb at blistering speeds down the hill. Since the creation of the polycarbonate gate, skiers have adapted. When going between gates, a skier will likely hit the gate and knock it out of the way in order to achieve the fastest line. Back in the day, skiers would hit the gates old school, which is where the skier uses their back and arm to blow the gate out of their way and keep their line towards the next gate. Nowadays, skiers crosswalk. This is the action of a skier hitting the gate with their poles and having the gate go completely under them. Crosswalking allows the skier to get closer and closer to the gate and be able to turn less, causing faster and faster times. Okay, so let's answer some of the questions with physics in mind. The first question being, how does one generate speed while skiing? Is the skier just using gravity to propel themselves down the hill, or is there something else there? Well, the first that should be noted is that rather than simply using gravity and the slope of the hill to generate speed while skiing, an advanced skier is able to use their muscles throughout their body or chemical energy to generate speed by bending the ski and using that energy to propel themselves faster and faster down the hill. Let's observe one of the most talented skiers in the world. Marcel Hirscher starts the top of his turn by applying pressure to his ski and then later releasing that pressure to let the skis glide and increase velocity as he moves from gate to gate. The energy transfer is as follows. Obviously, there is no work involved in this system because it is defined as the Marcel plus skis system. Marcel first uses his chemical energy and the energy that is already there from gravity to load the ski with the elastic energy. At the bottom of his turn, he releases the elastic energy, which adds on to the already existing kinetic energy, thus increasing his velocity exponentially. The second question that needs to be answered is if the impact hitting the gate is slowing him down enough to affect his velocity. To do this, we must first understand momentum. Momentum is defined as the letter P in physics and goes as follows. P equals m times v, mass times volume. Momentum is a vector, so that means that it has a direction. For simplicity's sake, we will define the direction as downwards. Now, we need to calculate the resulting velocity of the combination skier and gate after the collision. To start, we need to find the combined momentum before the collision. And to do this, we will use Marcel Hirscher's weight, speed, and the weight and speed of the gate. A simple Google search shows me that he weighs 75 kilograms, but we also need to find his speed. To do this, I used a video of Marcel skiing in a World Cup slalom race, estimated the distance between the gates by using the turning radius of FIS-regulated skis, and then timed out how long it took to move from one gate to the next. I then plugged these numbers into the formula for velocity, v equals delta d over delta t, and found that he moves at 13 meters per second between gates. I contacted a FIS-regulated alpine skiing gate manufacturer to get the exact weight of one of their polycarbonate 30mm in diameter FIS-regulated ski gates. The manufacturer told me that a single gate weighs 485 grams, or 0.485 kilograms. And we know that before the contact, there is no velocity of the gate, so v naturally equals 0 meters per second. Now back to momentum. We need to find the total momentum of the system, so we will do the mass of Marcel times the velocity of Marcel plus the mass of the gate times the velocity of the gate, m times v plus m times v. So we do 75 times 13 plus 0.485 times 0, so 975 plus 0, 975 kilograms meters per second. So, now we've calculated the momentum before Marcel hits the gate. We need to realize that the momentum of Marcel and the gate together has to be the same as the momentum as Marcel and the gate were when they were separate. Because the rule of momentum is that there's no external forces acting upon the system, momentum is conserved. So now we combine the mass of the two items, Marcel and the gate, which is now 75.485 kilograms. We will now use this to find the new velocity of the system. We use the momentum formula. Mass times the new velocity equals 975 kilogram meters per second. Now we solve for the new velocity by dividing both sides of the equation by the mass, 75.485, and we are left with the new velocity being equal to 12.916 meters per second. The gate only managed to take 0.64% of Marcel Hirscher's speed. So that is not that much. In fact, Marcel Hirscher, since he gains speed and gains velocity every time he turns by releasing the elastic energy from his ski, from the kinetic energy from his thighs, he actually regains that really, really quickly. Having the gate there literally does nothing, especially at the speed that he's going. So I had this idea of seeing or comparing the differences between the amount of power that Marcel Hirscher makes versus the amount of power that Hafthor Bjornsson makes. And in doing so, I was able to figure out that, if Hafthor Bjornsson had the exact same amount of skill as Marcel Hirscher in skiing, he would be able to output a lot, and I mean a lot more power. Here's how I did it. First, I started with Marcel Hirscher. I found his kinetic energy, and in order to do so, I used the formulas. So 1/2 mass velocity squared equals 1/2 his mass is 75 kilograms times 13 meters per second, which is the velocity that we determined earlier. This ended up equaling 6,337.5 joules. And we know there's an energy constant that goes around, so his kinetic energy, or his total energy, let's say, we're going to do like net energy, that ends up going through him, so gravity and his chemical energy go into elastic energy into his skis, and that is eventually put into kinetic energy. So his chemical energy, or his total chemical energy, is equal to 6,337.5 joules. So to figure out the amount of power that Hafthor Bjornsson, or, again, the mountain from Game of Thrones, creates, I watched a video of him benching 200 kilograms for 10 reps. I used the work equations, so I found the variable F net equals mass times acceleration. The mass is obviously 200 kilograms. Acceleration, this was a little bit more difficult. In order to find this, I had to find delta D, and delta D was equaled 14 meters. I know this because I used the concept of the Vitruvian Man. So obviously for delta D, we need to figure out how much distance the bench, or the bar that he was benching, has traveled. In order to do this, I used the concept of the Vitruvian Man, because there's no actual measurement of Hafthor Bjornsson's wingspan online, believe it or not. And I made a guesstimate that his bench press height would be 0.7 meters tall. I multiplied that by 20, ended up being 14 meters in total. So that's how I got my net force to equal 9.8. Then, 9.8. Then what I did, obviously work equation, force times delta D times cosine. Cosine is equal 1 because it's just going up and down. So what I did, 200 times 9.8 times 14 times 1,
ended up equaling 27,440 joules. So in the end, Hafthor Bjornsson would actually, have. Oh, sorry. In the end, Marcel Hirscher only outputs about 0.2% of what Hafthor Bjornsson outputs in joules. And yeah, I guess that just goes to show how a 190 kilogram man, compares to a 75 kilogram man. Yeah.